Welcome everyone also from my side to this last day of the semester. I'm happy to be here and tell you a bit about quantum communication and more specifically about quantum key distribution. And I hope that works. Yes, okay. Let's hope it's stable. Yes, if you have any question, please interrupt me at any time. I'm happy to answer all the questions you have, and I hope you will understand what I'm going to present to you. I'm going to start with a bit of an overview and introduction to quantum communication. So generally, quantum communication is like a huge field. It entails lots of different aspects. And in principle, you could fill like a whole semester worth of courses about quantum communication. And actually, you could fill several courses with all these individual topics on quantum communication. So these are just like some examples of what falls under the umbrella quantum communication. So that would be quantum cryptography, it's also quantum random number generation, it's quantum networks, cloud computing, also error correction, and generally communication channels for quantum communication. So we'll not talk about all of these topics in this lecture because then we would only like scratch the surface of each one of them. So we'll focus on few topics more in depth. And specifically, I will focus on the quantum cryptography part because that's where my expertise lies. And generally, you could sort all this, everything that falls under quantum communication into two types of protocols. So they are the ones that use quantum to enhance the efficiency of protocols, where, for example, you could say that super dense coding, where you can transmit 2 bits of information in one use of the channel. So that's classically, you could only transmit 1 bit per use, and quantumly you can double this, but you of course need a quantum channel, so that would enhance the efficiency of the communication. A second example could be quantum source coding, which allows you to efficiently compress quantum information. And then there's the second type of protocol, which uses quantum to enhance the security of protocols. And here, one very prominent example is quantum key distribution. That's one of the more mature technologies in this area. Here you use quantum principles to show the So you use quantum principles to show that a communication protocol can't be broken, that it's unbreakably secure, and in that way you reach a higher standard of security from quantum principles. Another example is quantum random number generation, which allows you to generate provably unpredictable numbers. And the third example would be cloud computing, which allows you to send a computation to a quantum server in a way that the quantum server doesn't learn about this. So these are all examples where you want to enhance the security of a protocol in a way that you couldn't do it with any classical means. And I want to go a bit, give you a few more detailed examples, so you see a bit what the landscape is of protocols that you could do in this area, and also where the limitations are and what usually is the focus of the analysis of such protocols. Okay, so as I said, I want to focus on security in quantum communication, so on the quantum cryptography part. And here, let's first say, what do we mean when we say we want something to be secure? We want a protocol to have some sort of security guarantee. Should I use it or?
Yes.
Yeah. Okay. Yeah, that works. Okay, so typically in any sort of communication protocol, we have 2 types of parties in the protocol. There are honest parties, which could be one or multiple parties, which want to honestly perform the protocol. And we have an adversary, or maybe also multiple adversaries. And then there could be different kinds of protocols. So it could be that an honest party wants to perform a protocol with the adversary, so he doesn't trust the other party. It could also happen that 2 honest parties want to perform a protocol with each other in the presence of an adversary. And of course, also multiple parties could perform a protocol together with an adversary. And then the goal of what you want to say about these protocols is you want to have some sort of security guarantee. So each of the honest parties wants to have some guarantee that about the protocol. So they want to know how much the adversary can learn about it or what could go wrong in the protocol. Of course, it could also happen that two dishonest parties want to perform a protocol with each other, so each party doesn't trust the other one. And even then, they want to have some sort of security guarantee about the protocol. So what is the worst thing that could happen when the protocol is performed, if the other party is dishonest? Okay, and the general structure to reach such a security guarantee is that the parties would start with some assumption about the protocol, for example, about the resources they have, about the ways how the protocol is performed, about the powers of each involved party. And then they do a security proof for the communication protocol and they reach a security guarantee. Okay, let's look at how this would look like for some examples. So one very basic building block of cryptography is something called oblivious transfer. And here the idea is that you have a party Alice, which for example has a server full of data. In this example, the data consists of like two different elements just, but generally it could be a huge amount of data. So she has two different bit strings, SA and SB. And Bob wants to learn a bit string, like either SA or SB. So he chooses the bit A or B and tells it to the server. And he wants to retrieve the respective bit string. Okay, so it would be like a user queries a database and wants to learn one element of the database by saying like which element he or she wants to learn. Okay, and this is an important building block because it is universal for two-party cryptography. That means any sort of function evaluation between two parties, it can be built just from this protocol if it fulfills certain guarantees. So what the two parties want to achieve is that first, Bob wants to receive the correct bit from the database. When he says he wants to receive SA, this is what he should receive. Then Bob is not supposed to learn any of the other bits. So it's not, he can't just get the whole database at once. He needs to restrict to the bit he actually required to ask for. And then Alice is not supposed to learn which bit Bob has received. So each party has some sort of guarantee about what the other party learns or doesn't learn. So the user doesn't want the server owner to learn what they ask for, but the user also cannot just ask, like, cannot get all the data at once. These are the guarantees that we need for this protocol. Then is the question, like, can this be achieved in any way? So first, classically, it can only be achieved if there are made certain computational assumptions about the involved parties. So there's no protocol that just works classically where Alice and Bob have like unlimited computational power. But maybe quantumly we can achieve something more without, like, with less assumptions. And sadly, even quantumly we cannot achieve this task without any assumptions. So there are protocols that implement it using quantum states and quantum measurements, but Bob has to have a bounded quantum memory, for example, for this to work. So you see, the issue with the security of protocols is not like usually you say, okay, you want to achieve this sort of security guarantee, this is the objective that I want to achieve, and then you ask yourself, what are the assumptions that I have to make in order to be able to get these guarantees? And sometimes you have to make like strong assumptions. For example, if you want to stay classical, you have to make computational assumptions, or you have to say something about the quantum memory of the parties that are involved. And then you can ask yourself if you're happy with these assumptions as a user. So you know, if you have to make this assumption, then you can ask yourself, okay, do I think this assumption is fulfilled? Or can I show that this assumption is fulfilled? And if yes, then I can safely use this protocol because then I get these security guarantees. Okay, there's a second example that I would like to mention, which is blind quantum computing. And this is something where Bob has a quantum computer and Alice wants to run a quantum computation. She doesn't have a quantum computer herself, but she can delegate computations to Bob. And usually she would tell Bob some sort of input state and the quantum circuit that he should run for her. And then she wants to get back the output of the computation. Okay, the security guarantee that we want to have for blind quantum computing is, of course, Alice wants to receive the correct output that corresponds to her computation. And she also wants Bob not to learn anything about this computation or the output or the input because it's blind. So you don't want the server to learn anything about what you're computing, but you still want to get the correct output. And this is blind quantum computing. Okay. So yeah, classically you can't do such a thing as classical blind computing, but quantumly this is possible if the user, Alice, can prepare and send quantum states. So the user needs to have some sort of like quantum source that can prepare quantum states that are sent to Bob. So she also needs a quantum channel that connects her with Bob, which might be a bit unrealistic if you think like you're a user who wants to run a quantum computation at some like cloud service. Then you at home, you don't have a quantum channel, that's a quantum source that's connected with the quantum computer. You're a classical client. So ideally, what we would like to have for this is that a classical client could do the same thing. But sadly, if you're a classical user, then you again need additional assumptions. So for example, if you're a classical user, it works if there are two quantum computers that don't communicate. So here, the assumption would be that the quantum computers are not communicating, which is something you might not want to believe because you don't know these parties that run the quantum computers. You can't guarantee that they don't communicate. But it's an assumption you have to make if you want to realize this protocol with a classical user. Okay, so what these examples are supposed to illustrate is that like with quantum communication, there are different types of protocols that you can think of that where you can enhance the security of the protocol by using quantum resources, quantum principles, but it's not like a solution for everything. So there are even limitations if you have access to quantum mechanics. And to realize the protocol that you want to realize, you might have to make some assumptions about the parties involved. And this is also the case for quantum key distribution, where we come to later. Okay, so the quantum key distribution more generally falls under the area of secure message transmission, where the general setting is that we have these two parties, Alice and Bob, and these are honest parties in the quantum key distribution protocol or in the secure message transmission. So we have the two honest parties, Alice and Bob, and then there's a dishonest party, Eve. So everything everything the adversary does is entailed into what Eve is doing with the protocol. And the goal of a secure message transmission protocol is that one honest party wants to send a message to the other honest party via a communication channel in a way that the adversary doesn't learn about the message. Okay, of course, this is a task that is like everywhere in our daily lives. Like if you communicate, if you send WhatsApp messages, if you send emails, if you communicate with your bank or do online shopping, everywhere you want to encrypt messages. You don't want outsiders to read the messages that you're sending, because it could, for example, be your bank data. So of course, classically, there are algorithms that achieve this. And one of the most famous ones is the RSA algorithm, which is still in some form nowadays used quite widely. And here the basic idea is that there are two keys. Bob, he generates two keys. One is private, that's only known to Bob, to no one else. And the other one is public. That's something he can actually put on his website for everyone to use. And then if Alice wants to send a message to Bob, she would take the public key, encrypt the message, and send this encrypted message to Bob. Bob can decrypt the message because he has the private key. But any outsider who reads this encrypted message cannot decrypt it because you need the private key for this, and this is only accessible to Bob. Okay, so the security of the scheme comes from the following structure. So the public key is generated by using two large prime numbers, which are randomly chosen, and they're multiplied. So only the result of this multiplication is publicly known. That means, of course, if you could factorize this large number that is the result of this multiplication, then you know the individual factors, P and Q, and with this you could calculate the private key. So it's not impossible to get the private key. It's just that to achieve this, you would need to be able to factorize large prime numbers, and this is something that is known to be inefficient on classical computers. So here, the assumption that you put into the protocol to get the security guarantee is that factoring large numbers is hard for a classical computer. But we also know, since Shor presented his algorithm, that it's not hard for a quantum computer. So this is a case where for a long time people believed this is a reasonable assumption, we can believe this. our security guarantee is safe with this assumption. But then someone came and showed that the assumption might not be justified if the adversary has access to a certain kind of technology. Okay, so since we know it's not hard for a quantum computer, so a quantum computer could break this, people have started to look into alternatives for this. You see. And a bit more generally, you could look at the security of such classical encryption schemes in the following way. Like on the x-axis, you see time, and on the y-axis, you see the probability that the encryption scheme is broken. And here I've put the graph for the RSA algorithm. So if you start using the RSA algorithm, you would choose all the parameters in a way that the probability for it to be broken is very small. But then over time, there are some evolutions, like hardware gets better, so it might get a little bit more insecure because your computers are faster. There could be some small algorithmic discoveries that improve algorithms for factoring, so there are some little jumps that also make the probability a bit higher that this scheme gets broken. And as I said before, the quantum computer could break the RSA scheme. So as soon as you have a universal quantum computer, your scheme just immediately gets insecure, and then it stays insecure. So this is like the fate of a classical encryption algorithm. And even though, even if you have a classical encryption algorithm where we don't know yet whether a quantum computer could break it, people could still any day come up with some sort of algorithm that could break the scheme. So this could generally be the fate for all classical encryption algorithms. We just, we can't be sure that it stays safe. In contrast to this, you have quantum protocols for secure message transmission. And a quantum protocol would just stay on the same level, the same time, because the security of the quantum protocol does not depend on algorithmic properties or on how fast the hardware is. It just depends on the principles of physics. And as long as the laws of physics stay the same, the quantum protocol will be equally secure. Okay, and this is the part where we want to go into more detail now. And this is where quantum key distribution comes in. Okay, now I will start to write down things, if I can. Yeah, perfect. Okay. So now I want to learn a bit more about how we can realize this secure message transmission protocol using quantum principles. So, okay, so generally, as a reminder, what we want to do is we have this party Alice. Yeah. And Bob. And she wants to send a message M to Bob such that he can retrieve the message and the message does not go to Eve. Okay. So the first thing to notice is that this is possible to achieve classically. So there is a classical protocol that achieves this with perfect security. And this is the so-called one-time pad. And the idea here is that Alice and Bob, they both also have a key, K. So that, like on Alice's side, she has this message, which is, say, 5 bits. And she has a key. Say this is the key. And then the encryption procedure of the one-time pad is that she just adds the 2 bits. That's bitwise addition, so we have here this outcome. And this is called the ciphertext. And then the ciphertext will be sent over the this communication channel. Okay, and then Bob receives it. So on Bob's side, he gets the ciphertext. And he also has the same key as Alice. Oh, what's wrong? This is the ciphertext. And to decrypt the ciphertext, he just has to do the same operation. So again, he adds all the bits. So you can see Bob did get the same message that Alice sent to him. So the encryption scheme, it works correctly. With this procedure, Bob will get exactly what Alice has sent. But the question is the scheme also secure? Okay, so the scheme is secure if the key fulfills certain properties. So you can't just use any key. Okay, the key, it has to be uniformly random. And we'll see in a second why that is necessary. And being uniformly random means that each possible value the key could have is equally likely to appear. So let's say the key has a length of L bits, then each possible L bit string appears with equal probability. So an adversary who wants to guess the key has no information about which of the possible keys it is. Each possible key is equally likely to appear. Then the second property is that it is identical for Alice and Bob, which is required for the scheme to work correctly. And the third property, of course, is that the adversary doesn't know the key. Okay, so why is the scheme secure with these properties? Okay, so what is important, what is required for security is that the ciphertext does not contain any information about the message, because the ciphertext is public, it will be also known to the adversary, so it shouldn't contain any information about the message that Alice wants to encrypt. And mathematically, what is required to show for this is that the probability distribution over the space of messages given the ciphertext, like the probability of having a certain message given the ciphertext, is equal to just the probability of the message. That means if Alice, so if the adversary wants to guess the message, then it doesn't help her to know the ciphertext. This is what this condition on the probability means. So in turn, it means the ciphertext does not contain information about the message. Okay, and to show this is just a quick calculation with probabilities. So you start with looking at this probability, the probability of having a certain ciphertext given the message. And when you look at how the ciphertext is generated, then you see, as above, it's just M plus K. And if you rearrange the equality a bit, you can write it as k is equal to c plus m. So you just put the m on the other side. And then what you have here is the probability of a certain key given the message. And we have the property that the key is uniformly random. That's one of the requirements for the key, which means if the key is chosen uniformly at random, it doesn't matter, like every key value is equally likely, and that means the probability for each individual key is 1 to the power of 1 over 2 to the power of L. So L is the length of the key. Okay, from this it follows that, so this is just a calculation with probabilities. We want to the probability of a certain ciphertext. You can write it like this, with a sum over the messages, and then you can put in what we've just calculated. So this is 1 over 2 to the power of L. Then you have this sum over the probability of all messages, which sums to 1 because it's a probability distribution. So the probability for a given ciphertext is 1 over 2 to the power of L, which means each ciphertext that can appear is equally likely. And then and then if we put this together, since this holds for all messages, and say the probability of a message given the ciphertext, which is the property here that we want to look at, just by some basic laws of probability, we can write it like this, as the joint probability of the message and the ciphertext over the probability of ciphertexts. And this we can write like this. And then we just put in what we have calculated before. Yes, please.
One question. So I understand that it would improve the security, but it's strictly required to have the uniform distribution of probabilities?
Yes.
But if it were just a little bit shifted, that would make it absolutely completely insecure.
It would allow the adversary to learn something. And it's difficult to quantify what exactly the adversary learns. So with this, if these properties are fulfilled, then you have the guarantee the adversary learns nothing. Yeah. Okay, so yeah, if we put in what we've calculated before, we have this 1 over 2 to the power of L twice in the for this here and here. So what's left is the probability of the message. So you can see this is exactly what we wanted to show, that the probability of distribution over the messages is the same as the one over the messages given a ciphertext. Means it doesn't help the adversary to to know the ciphertext for learning anything about the message. Okay, so this means that so M is independent of C. So it's safe to let the adversary know C. Okay, so this is a classical scheme that you can use to encrypt messages in a way that no one can learn the content of the messages. But of course, the key has to fulfill these properties. And this is the big challenge. How do you generate a key that has these properties? Because Alice and Bob, they are two parties which are in principle distantly apart. They're very far apart. And they want to establish this key just by communicating with each other. They don't want to. You want to avoid that they have to meet to exchange a key, before they can communicate securely. You want a way to establish a key for such that the parties can remain at their two distant locations. And classically, this is impossible. And this is where quantum key distribution comes in. So the goal of quantum key distribution is to generate such a key that allows you to perform this one-time paired encryption afterwards. Because also any scheme that is perfectly secure, that cannot be broken, has to fulfill these properties. So you can't really do better than this. A little disadvantage of this encryption scheme is, of course, you see your key has to be as long as the message that you want to encrypt. So you need a lot of key for this. And you can never reuse the key. So once you've used it once, you have to throw it away and you cannot reuse it. So it's very, it has a high demand on amount of key that you need to generate. But there's no scheme that can do that uses less key and has the same security guarantee. So if you want an unbreakable secure scheme, you have to generate this large amount of key. Okay, and now I want to look into how exactly we can generate this amount of key by using quantum physics. Okay. Let's see.
Can I ask a question?
Yes, please.
When you say there is no key, do you mean, or there's no way to do it with less key? Does that mean no way has been found, or does that mean it has been proven that it's not possible to do it with less key?
It has been proven that it's impossible.
Okay.
Yeah.
Thank you.
It's like a paper from 1949 by Claude Shannon that says the key has to be at least as long as the message for it to be perfectly secure. Yeah. Okay, so first we want to look a bit into the properties of quantum physics and investigate what part of quantum physics we can use to actually ensure security, so to be able to generate a key that has these properties. And if you want to read something more about this, there's a paper that is co-authored by me, which explains these quantum phenomena for QKD a bit on a higher level, such that not too technical, but it gives a nice overview of which elements of quantum physics we need for security. Okay, so of course, you all probably had some sort of quantum mechanics course in your studies, and what's done in the quantum mechanics course is a lot of Schrödinger's equation or calculating potentials or something. But for the security of QKD, we don't need any aspect of time evolution at all. Actually, the Schrödinger equation doesn't play any role in quantum key distribution. What we're looking at is the structure of the state space of quantum states. So we're interested in the properties of the quantum mechanical state space. So, and very simply, the setting that we want to investigate here is that we have some source of quantum states. Here's a quantum state psi. And then we have some measurements. Which produces a classical measurement outcome. Okay. And by investigating the properties of these quantum states and measurements, we'll see how this allows us to generate a secure key with the required properties. Okay, so the most important example, which we will focus on in this lecture, is of course the qubit. So for a qubit, you have two possible states. So your Hilbert space C2. And you can choose different ways to describe a qubit. So you can choose different bases to write down the quantum states of the qubit in. So we need two different bases for this lecture. So you can use the computational basis, which I will also call the Z basis, because it's shorter. And here you just label the states with 0 and 1. And for example, you could represent those as vectors in R2. So these could be your basis states for the qubit. And the other basis that we need is the Hadamard basis, or X basis for short. Here you label your states plus and minus. And they're related to the computational basis in the following way. So these are the main bases that are used in QKD. Okay, so we can not only use the bases to describe the states, the quantum states. So, for example, like a general state in these bases, you would write your psi as some alpha plus some coefficient beta with 1. So this is a general qubit state. But you could also use these bases to write on your measurements. So you could also measure in the same basis. So if you want to measure in the Z basis, your projectors that you use, so you have one for the 0 outcome and one for the 1 outcome, and similar for the X basis. So for now, that's all we need. We can describe our quantum states in these spaces, and we also can describe our measurements in these spaces. And then let's look a bit what happens if we prepare quantum states and measure them. So let's look at some examples. Of course, quite trivially, when you have a quantum state that you just prepare in the 0 state, and then you also measure in the same basis, then what you will find is for the probabilities, so the probability of getting the outcome 0, you can calculate with your state and the corresponding projector onto the 0 outcome. Yeah, and if you just put it in, you'll see this is just all zeros. So the probability is 1. That's what you expect, right? You prepare a 0 state, you measure in the same basis, you get a 0 outcome with certainty. And then, yeah, equally, the probability of getting an outcome 1 correspondingly has to be 0. And of course, you also see that when you calculate it. So then you have this is 0. Yeah, so this is exactly what you expect. Then, what's the first one? If we look at another example, let's prepare the state in the plus state. So this is a linear combination of 0 and 1. But then we measure again in the Z basis. Okay, now if you look at the probability of getting the outcome 0, it's a bit more complicated. So your state now looks like this. This is your measurement operator. Then again, you have the state. And when you do this whole calculation, when you put together all the corresponding scalar products, so you would have basically 4 different combinations that sandwich this measurement operator. So these two together would give a 0 because you have the 1 and the 0 here that come together. This gives a 0. This one gives a 1. This one gives a 0. So whenever there's a 1 involved, you will get a 0. And if you calculate this, you see the probability of getting the outcome 0 is 1/2. And if you do the same calculation for the 1 outcome, you also see that the probability of getting 1 is 1/2. So the measurement outcome is completely random. You cannot predict the measurement outcome at all. That means the property that we can write states in a superposition and then measure them will provide the randomness that we need in the key. Okay, so this is the first property of quantum mechanics that provides one of the guarantees that we need for the key. This is our source of randomness that we can use. And there's an interesting observation. So here you have like a perfect state, a perfect measurement, and you get perfectly random outcomes. But of course, in reality, nothing's ever perfect. So your state will not exactly look like the superposition, or your measurement will not exactly be the Z measurement. But this property of randomness is somewhat robust. And what I mean with this is that if we look at the third example, so if we again have the same state, plus state, but then our measurement is a bit different. So before it was the Z measurement, so it was just the 0 projector and the 1 projector. And now we have let's say a 0 epsilon projector. So epsilon is a very small number. So we have the 0 projector almost perfectly, but there's a little disturbance. So there's a little bit of the other projector mixed in. And the same for the 1 projector. So it's an imperfect measurement in the computational basis. And then if you do the same calculation and you go through the probabilities, you calculate these probabilities of getting 0 and 1, then you will see now getting a 0 is a little bit more likely, getting 1 is a little bit less likely, I think. Okay. So even though our measurement wasn't perfect, our randomness is still almost perfect. So it's a robust property, this randomness. That means even if not everything is perfect, we get some amount of randomness, and that will show to be enough for the protocol. It doesn't have to be perfect, at least if there's still some randomness that we can use. Okay, so that's the first element that we needed, which will provide the randomness for the key. Let's get to a second property of quantum mechanics, which you're probably also familiar with, which is entanglement. Because so far what we can do is we can produce random bits. But this is just like for one party so far. With this property, one party can just produce random bits for themselves. But now we want two parties to produce random bits in a way that they get the same random bits. And this is what we use entanglement for. So here, say we have still our two parties, Alice and Bob. Let's see what happens if they share an entangled state. So let's say it's a 2-qubit state, and it's one of the Bell states. So say they share this perfectly entangled state. So now we can see what happens if the two parties start measuring this entangled state that they have. Okay, so we have the state. And then Alice measures her part of the state. She measures her qubit. And she chooses to measure it, let's say, in the Z basis. So she gets one of two outcomes, either 0 or 1. Okay, so then on Bob's side, the state will be either the 0 state or the 1 state, because if Alice saw a 0, then the state can only be this one. And then Bob decides to measure something. So he can also choose between two different measurements. That next, yes, yeah. Alice could have chosen to measure in the X basis, of course. Yeah. And let's say we're in this root. So Bob's state is the 0 state, and he chose to measure in the Z basis, so exactly in the same basis as the 0 state. Then he will deterministically get an outcome 0. If he chooses to measure in the X basis, he will randomly get plus or minus. And again, if the state was a 1, if he measures in the Z basis, he would get a 1. If he measures in X, he would randomly get plus or minus. And you could do the exact same thing if Alice measures in the X basis. Okay, so what you see here is that in cases where Alice and Bob have chosen the same basis, that's this and this, they also always deterministically get the same outcome. So they just need to share a perfectly entangled state and measure in the same basis, and then they will get the same outcome. The outcome is still random, because here Alice's measurement outcome, this is random. So Alice and Bob get the same random outcome in both places. Yeah, and this also works if Alice chooses to measure it in the X basis, because you see, you can write this entangled state also like this. And then it's exactly the same calculation. Okay, so using entangled states, we see that Alice and Bob will get the same bits in both places. Okay, so if we go back to the properties about the key that we were stating in the beginning. So we can ensure that the key is uniformly random by measuring superpositions of quantum states. We can ensure that it is identical for Alice and Bob by using entanglement. What we still need to show is that the adversary doesn't know the key. How can we, what part of quantum mechanics can we use to ensure that the adversary doesn't get access to the measurement outcomes which form the key? This is something that we still need to investigate. And for this, we need to ask ourselves, how can the adversary gain information about measurement outcomes? Yeah, so we have here Alice and Bob. And if there was no adversary, then what they could do is just, Alice could prepare a quantum state, an entangled state, and send it to Bob, and everything would be fine. But of course, we have this adversary that's sitting here. And reading and seeing everything that goes over this quantum channel. So the adversary can intercept the quantum state and tamper with it. Okay, let's see, but what can the adversary do? Well, so one thing the adversary could attempt to do is just try to copy the quantum state and then keep one copy for herself and send the other one over to Bob. Okay, so first is copy the quantum state. So the adversary builds a little box. The adversary has a quantum cloner. It just takes the state and outputs 2 copies of it. That would be handy. But you probably know that in quantum mechanics it's impossible to clone arbitrary quantum states. So generally this is forbidden. But, and if this were possible, then Eve has exactly the same information as Bob. Okay, but yeah, luckily it's forbidden by the no cloning theorem. So arbitrary quantum states cannot be perfectly cloned. Okay, and this can be seen either with a mathematical argument, just from the linearity of quantum mechanics. This is forbidden. But more intuitively, a more physical argument, which I actually really like, is that you could see if you had access to such a cloner, you would actually be able to communicate faster than light. And you can see this. So let's say the state is the maximally entangled state that we had before. And Alice keeps one qubit and she sends the second one to Bob. So only the second qubit here is the one that will be sent over the channel. So if Bob had access to a quantum cloner, he could just multiply his part of the quantum state and then just take say he makes 1 million copies. Then he takes half of the copies and measures it in the X basis and the other half and measures in the Z basis. So Bob, he makes many copies. Okay, and then let's say Alice has measured her qubit in the Z basis. So let's say the outcome was 0. Then what Bob aims to do is he wants to learn this outcome. He wants to learn that Alice saw 0. And if he now has all these quantum states and can measure half of it in the X and half of it in the Z basis, he will see the probability distribution over that. So the probability, this is his Z basis outcomes. The probability of getting a 0, if he measures in the Z basis, he'll see the probability is 1. Because Alice also saw the 0. And the probability of getting a 1 is 0. When he measures in the X basis, you will see that the probability of plus is 1/2 and the probability of minus is also 1/2. Because the state that he has measured, or all of the states that he has, after Alice has measured in the Z basis and gotten an outcome 0, then Bob's states will all be in the 0 state. So he will see this probability distribution and he will deduce that Alice must have measured in the Z basis and seen an outcome 0. So Bob concludes Alice's outcome was 0. Now you can see Alice and Bob could have set it up in a way that they have distributed the state long before, so they have a reservoir of such states. And then they say, okay, now we want to communicate faster than light. So in that moment, Alice measures and Bob measures. And if they are very far apart, this measurement and this communication, this will be faster than what they could have communicated with the speed of light. Because they could sit on different planets. But this, for this measurement procedure to take place, they don't need to communicate anymore. So, since it holds for arbitrary distances, they could communicate faster than light. Yeah, now if you believe in special relativity and that you cannot communicate faster than light, this is a very convincing physical argument for why such a quantum cloning machine cannot exist. So you have two kinds of arguments that show you this cannot happen. Just the mathematical argument, if you just believe in the mathematics of quantum physics, or the physical argument with faster than light communication. Okay, so for QKD, this means Alice and Bob can be safe. They know the adversary could not just copy the quantum state. So if they want to interact with the quantum state, if they want to learn anything about the quantum state, they have to do something else than copying it. Okay, so of course another possibility instead of copying is that the adversary could measure the quantum state. I mean, she has free access to the state. So second possibility is that Eve could measure the quantum state. Okay, let's see what happens in that case. So let's go back to what Alice and Bob expect in their measurement outcomes. So we had this tree of measurements, which I'll copy here. Okay, so this is what Alice and Bob expect. If they have an entangled state, they expect to get exactly the same outcome if they measure in the same basis. But now the adversary intercepts the quantum state while it's traveling from Alice to Bob. So, say here at this point somewhere, Eve intercepts. Okay, and let's look at the example here. This one. So the adversary has intercepted the quantum state, so Eve's state that she has now she has this state 1. And now she doesn't know in which basis anyone has measured or prepared a state, so she has to randomly choose in which basis to measure the state to get information. So she will choose either the Z or the X basis. And then she'll get an outcome, of course. So if she measures in the Z basis, she will always get the 1 outcome. If she measures in the X basis, she'll get plus or minus with equal probability. Okay, so that's the information she now has. But of course she has to send something to Bob. Bob is expecting a quantum state. So the most straightforward thing that Eve can do, because this is the only information she has so far, is just encode the outcome she got again into a quantum state. So in this case here, she'll just send the 1 state. Here she will send the plus state, and here she will send the minus state. Okay, and then comes Bob. Bob receives a state, and he needs to decide what to measure in. So, yeah, he'll choose randomly again. X, Z. And he's getting some outcomes. Okay, so that's different order than before. Z and X. Okay, so if he chooses to measure in the Z basis, when he got the 1 state, of course, he'll get the 1 outcome always. If he measures in X, he gets a random 1, plus or minus. But for the other side, it's exactly the other way around. If he gets a plus or minus state and measures in the X basis, he deterministically gets an outcome. If he measures in the Z basis, he gets a random 1. Yes?
Sorry, but why is if state 1? I did not follow up.
This one above here.
Yeah.
This is one example. So Bob's, after Alice has measured, the state that is sent to Bob is either the plus, the 0 or the 1 state in this example. And then...
So Eve doesn't know per se this...
Yeah, exactly. Eve doesn't know. It's just if the state was 1, which I know, but Eve doesn't, then this is what happens to the outcome distribution. So in this case, you'll randomly get 0 and 1 for the Z measurement and a deterministic 1 for the X measurement. Okay. So what Bob is expecting is that if he measures in the same basis as Alice, he gets the same outcome as Alice. And here was Alice has measured in the Z basis. So Bob is expecting if he measures in the Z basis, he gets the same outcome as Alice. And in the case of the 1 state, Bob is expecting a 1 as an outcome. But as you can see, he measured in the Z basis here, here, and here. But he only deterministically gets a 1 outcome here. So in that case, he will be fine. This is what he expects. But sometimes he will see zeros. And this is what couldn't happen if there was no adversary. Without the adversary, there would be no zeros. There would always be 1s in Bob's outcome. So the presence of these zeros that sometimes happen, these zeros show that someone else must have intercepted the state, that it didn't directly come from Alice to Bob, that something has happened in between. So it's not longer true that measuring in the same basis gives the same results. So Eve's interception has introduced errors that Alice and Bob can see. Now, of course, you could say when Alice sends a quantum state to Bob, the quantum channel would not be perfect. There's always noise that could also change the quantum state in a way that there will be errors in the end, that sometimes Bob will not see the perfect result. And that's true. Practically, there will always be noise that can introduce these errors, but in cryptography, we're very, very careful and we're very paranoid. So all the errors that we see, we attribute to the adversary. So in principle, we attribute such power to the adversary that we say, okay, even if there is a noisy quantum channel, the adversary could in principle replace the noisy quantum channel with a perfect quantum channel. And then all the errors would be because the adversary gained information. This is, of course, unrealistic. It's super paranoid. But the problem is that you can never say where the noise ends and where the adversary starts. So if you really want to be secure, if you don't want to rely on your assumptions, then you just say all the noise, all the errors that we see are due to the adversary. And we don't care if it's noise or not. We're just super careful and then we're super safe. Yes?
So how does Bob know that an error occurred? Because he, in principle, does not know that Alice has measured 1, right?
Yes, true. So a bit later we'll see exactly how the whole protocol works, and then at some point you see that Alice and Bob communicate the basis in which they have measured. And then they will see, and they will also communicate some of the outcomes that they've seen. So they will use some of the rounds in the protocol as test rounds to estimate the error rate.
But will they communicate them classically?
Yes.
Okay, but then it would be possible for Eve to also intercept this classical information, then he could also measure in the same basis, right?
Yes. So that's so it's important what timing you have in the protocol. And I will show you the whole steps of the protocol later, and then you will see that it's important at which time this communication happens. Yes?
So I'm not completely sure, but does this happen because Eve doesn't know which basis does he have to use for measuring?
Exactly. If she knew which basis Alice had used, then she could measure in the exact same basis. So then she could just always be in this part of the tree. And if she knew that the basis was that. And then Bob would see no error. So it's important that Eve doesn't know the basis that Alice has used. Okay, so we see Eve can get information about the key by measuring it, but she will also introduce errors, so she can't do it undetected. Then there's a third possibility that can happen, is that instead of measuring the state, Eve can also entangle herself with the quantum system. Okay, so we have, let's say, Alice and Bob, they use this entangled state. And we've seen that if they use this entangled state, an important property is that they always get the same measurement outcomes. So the question is, could Eve just like entangle herself with the quantum state and then also always get the same measurement outcome? So like somehow she has some state that's also entangled with Alice and Bob's state. So this would be Alice and Bob. So then in the statement, you would just say Alice and Bob and Eve always get the same outcomes when measuring in the same basis. And that way, Alice and Bob wouldn't see any errors, and Eve would have exactly the same information as Alice and Bob. So this could be the perfect attack for her in the scheme. But again, quantum mechanics saves us here with its properties. So this is forbidden by the monogamy of entanglement. So if you have two parties which are perfectly entangled, then they know they are in a product state with any third party. So if Alice and Bob have this quantum state above, they know that it must be like the state of I'll write it. So the state of Alice, Bob, and Eve, it has to be of such a form. If this is Alice and Bob's marginal state. So this is forbidden by the monogamy of entanglement. And there is really no three-party state such that all three parties would always get the same measurement outcomes when measuring in the same basis. This kind of state does not exist. Okay, so, and this is, for once, like it's a mathematical argument that you can make, but also a physical argument, again, would be that if, like, polygamy of entanglement would be possible, then this would allow quantum cloning, actually. So, yeah. This could be possible via quantum teleportation. So that's a protocol that allows you to basically teleport one quantum state from one party to the other when they share such a maximally entangled state. Because then, like, one party could share a maximally entangled state with two other parties and teleport this state, like the same state, to both other parties. And then those two parties, like the first party would have one state, but then it would be copied because both other parties would have this state. I will not explain this in detail here, but this is, for example, explained in the paper I mentioned before. polygamy of entanglement would allow quantum cloning, which in turn would allow faster than light communication. So it can't be possible to have polygamous entanglement. Okay, so these are the ways that that Eve could gain information about the key. And if we summarize what we have learned from quantum physics about the security of our key, like when we go back to the properties that we wanted to achieve. So what we wanted is that key is uniformly random. Then we've seen that from the superposition of quantum states, we get the randomness. We wanted to have identical keys, which we got from entanglement. And we wanted that the key is private. And here a variety of properties were important, like that quantum cloning is impossible. That entanglement is monogamous. And also that measurements introduce disturbances. So okay, so these properties of quantum mechanics, they ensure that we can produce a key with the desired properties. And all these properties that I showed you, they are part of the structure of the state space of quantum mechanics and also about measurements of these states. Okay, so these are the ingredients that we need to design our protocol. And now I want to show you in more detail how exactly the protocol looks like. So what the steps are that Alice and Bob have to perform in order to ensure that everything works out, that the adversary doesn't get not any knowledge about the key, and we use these properties of quantum mechanics in the right way. Yes?
I have a question for the monogamy of entanglement.
Mm-hmm.
Let's say Alice doesn't create her own qubits. We know that there are GHZ states where the three of them are entangled.
Yeah.
So I was wondering, wouldn't that be a big flaw?
No, because for the GHZ state, this property is not fulfilled. They actually, so what's important is if you look at the reduced state of Alice and Bob, then this is not a maximally entangled state anymore. So Alice and Bob wouldn't get the same measurement outcomes when measuring in the same basis, so they would see errors.
So they would have a way to figure out that they were using a GHZ state?
Exactly, yes.
Mm-hmm.
Yeah, so if Eve just replaces the state by a different state that has entanglement between three parties, Alice and Bob could detect it with the errors. Yeah.
Okay, thank you.
Okay. Right. Yes? Okay.
Yeah, I wanted to ask about, so for the classical case, we had something to say about the length of the key.
Mm-hmm.
That was suffix C2C, which means the key to be as long as the message.
Yes.
Is there something that we can infer from this about the length of the key?
So these, the measurement outcomes will be used to generate the key, and you will have to do as many measurements as message bits that you want to encrypt.
So in that sense, you're not really reducing the length of
No,
the key.
no. So this, we don't want to use quantum mechanics to reduce the length of the key. We just want to use it to ensure that the properties are fulfilled, like the randomness and the secrecy and everything. But we can't get around the issue that we need a lot of key. Yes?
So just the previous question regarding the entanglement between three different parties, you said that it can be intercepted, like Alice and Bob would know that it's, but in this case, Eve cannot really do this state in any case because the state is already entangled. So what I understood from the monogamy of entanglement correct me if I'm wrong, is that we can't really because we can't really write an entangled state as a product state, right? So that's the idea. So what?
I think what the question was aiming for is that, like in this case, I said Alice prepares the state and sends one part to Bob. But in QKD protocols, you sometimes have it that there is a source that sends states to Alice and Bob, and the source is given to the power of the adversary. So then, in that scenario, the adversary could just prepare a different kind of state.
Okay.
Right. So then, let's. Yes.
Do you have an example where even in a GHZ state, if they use the same basis, they don't get the same outcome?
I think you can just, like, if you just take the, if you calculate the reduced state for Alice and Bob from the GHZ state, and then do this kind of calculation, like you put the projectors, like you just calculate the probabilities with the projectors for measuring in the Z or X spaces, you will see that.
But you don't have a quick example?
No, I would have to think for a moment to make it right. Sorry.
Thank you.
Yes?
I was wondering if this could be extended to like share the message between two parties, like using like the GLZ state or something.
I was like, for if you have multiple parties who want to, yes, actually there are protocols for like multi-party QKD where more than two parties want to establish a key. And in some scenarios, it is beneficial to have like a GHZ state, for example, for for three or more parties to establish a key. Yes, that's true.
Does it work on the same protocol, or like do we have to consider some other?
The protocol is quite similar. You just have to make some additional security, like the analysis of it is a bit more difficult because you have more parties. But yeah, the principle is very similar. Right. Okay, so then let's look at how exactly the steps of the protocol are to see what we need to take care of in terms of timing and which information is communicated. So now we want to see an example of a QKD protocol. Okay, and for this I will present to you the very first QKD protocol that has been invented, the BB84 protocol, because actually it's nowadays still the most important protocol. So it was invented in 1984, BB84, by Charles Bennett and G. Brassard. And they did such a great job with this protocol that it's still nowadays the basic protocol that is used in many applications, and there have been like different kinds of protocols have been built from this protocol. So it was a very genius invention. First, let's look at the exact setting of our protocol. So let's look at what Alice and Bob have in their labs and what kind of resources they have that they can use to generate the key. So let's see, here we have Alice's lab and we have Bob's lab. Okay, so in Alice's lab, she has a source, quantum source. So she can prepare quantum states. And she has a measurement device. So what she will do is she will prepare a quantum state that comes out of the source, psi AB. One part will go into her measurement device and the other part will go out of her lab and be sent to Bob. What she also needs is a classical computer. This one can store and post-process the measurement outcomes. Oops. Oh, that was stupid. Give me a second. to call this A. Okay, and Alice also needs a random number generator, because as we have seen before, she needs to do some choices randomly. For example, which measurements she does. So the random number generator will put some randomness for the measurement device, and also the classical computer needs some randomness for post-processing of the data. Okay, and with all of this, eventually the classical computing device will output the key on her side. Okay, and then this quantum state that she has prepared will go through to Bob through a quantum channel. So Bob receives this state. He has a measurement device. He also needs a random number generator that generates random bits to choose the measurement. He also has a classical computer. And in the end, this will output the key on his side. And of course, the two parties can also communicate classically. And here is where the adversary sits. Okay, so Alice and Bob, they have access to two different kinds of channels. So there's a quantum channel, which is just completely public. And the adversary has full access to it. So Eve could just intercept the quantum state and do everything she wants with it. And then we have the classical channel. And this has the addition that is authenticated. That means it is public, so the adversary can read everything that is on this channel, but the adversary cannot change the messages. So when Bob receives a message over this classical channel, then he knows that the message came from Alice, and also that this is exactly the message that Alice has sent. Okay. Okay, so this is the general setting that we have. These are the building blocks in Alice and Bob's lab, so they can use to then perform the protocol. Okay, so then let's go through the steps of the protocol. So the first step is that Alice creates a quantum state in her lab and sends one part to Bob. So Alice creates the state, this maximally entangled state that we had before. Keeps the first system, sends the second one to Bob. And the protocol will generally have many, many rounds, so this happens many times. But for this example, I will restrict the protocol to 10 rounds. So, okay. So in the second step, Alice chooses the measurement basis. Okay, so we have 10 rounds. And she does this randomly. And it's important that this choice is made randomly because we have to ensure that Eve doesn't know these bases. If Eve knew these bases, she could just measure in the exact correct basis, and we need to prevent that. And so it's important that we randomly choose this because we want to guarantee that it's fundamentally impossible to break this encryption. So the security is based on just like the laws of physics, more or less. So we can't make any arguments of saying, okay, it doesn't have to be random as long as only Alice knows it, as long as it's secretly hidden in the lab. Then we would add an assumption, the assumption that the adversary has no access to this knowledge. But if we fundamentally randomly choose these measurement bases, then there is no way, based on the laws of physics, that the adversary could have known them. Okay, and then Bob also chooses his measurement basis. He also does it randomly and independent of Alice. Okay, so this will look a bit different generally. Okay, and then Alice and Bob both measure in these bases and get some outcomes. Okay, so let's say Alice just measures in these bases, gets some random outcomes. Just choose some. So now for simplicity, so the X basis was this plus or minus basis, plus and minus. Now we will translate the corresponding outcomes also to bits 0 and 1. Because in the end, Alice and Bob need bits for the keys. So we say plus is mapped to 0 and minus is mapped to 1. That means here, if Alice gets a minus outcome with the X measurement, she will assign a 1 bit to it. Let's say these are her outcomes. And then in case Bob has chosen the same measurement basis, he gets the same outcome. Because so far there's no adversary. So this is the protocol as it would happen if no adversary was present and no noise, everything's perfect. So if they have the same basis, they get exactly the same outcome. So these cases. And if Bob has chosen, well, it's a lot of same basis. If Bob has chosen a different basis, then his outcome will be random, and sometimes it will be the same as Alice's outcome and sometimes not. Let's say this is one. So this is how the outcomes of Alice and Bob could look like after the measurement procedure. And this is the quantum part of the protocol. So this is quantum. Okay, and this is actually also the only quantum part of the protocol. So they create states, they measure them, and they get outcomes. After this, to make a key out of these outcomes is a purely classical procedure. Because now they have classical bits, and they can post-process these bits. But because they know these bits have been generated via quantum states and measurements, they can say something about how much the adversary can know about it. Okay, so now comes the classical part. in the first step of the classical part is that Bob announces his measurement basis. Or more precisely, he announces his measurement basis. So he will just take this and send this to Alice. So then Alice has the knowledge about all of these measurement bases. Of course, she knows her own measurement bases, and then she also knows Bob's. So she can check in which rounds they have measured in the same basis. So she will check this and tell Bob. So Alice confirms the correct ones. So we have this was correct. This. And these were different bases. So you can see the timing here is very important. Bob has only announced these bases after the whole measurement procedure has been finished. So now Eve cannot do anything anymore. At this point, she already had to interact with the quantum state. She already had to send something to Bob. So she doesn't have the quantum state anymore. Okay, so at this point, it's safe for Bob to announce his bases and for Alice to confirm which are the correct ones. And then they have the knowledge about in which rounds they measured in the same basis. So they only keep these rounds. They just discard the other ones because here their outcomes are completely uncorrelated, so they can't use this data. And then at this point, the shared information between Alice and Bob are these bits. Okay, so now Alice and Bob have to check for errors. So far they only compared their bases. So to check for errors, Bob will just reveal some of his bits. Okay, let's say he reveals this one, and this one. Okay. Then Alice compares the bits Bob has revealed to her own bits. And tells Bob if she has seen the same one. So in this case, we didn't have any adversary, any noise, so she always got the same bit as Bob. So yay. Everything's fine. Bob gets this information, sees okay. We haven't seen any errors, everything's all right. So they can use the rest of the bits to generate the final key. So the final key will then be, oh, I forgot this bit. Here. Well, then, oh, no, sorry. These ones. Okay. Okay, so in the end, Alice and Bob, they have 4 bits of key from these 10 rounds because they needed, in some rounds, they didn't measure in the same basis, so they needed to discard them. Some rounds, they needed to check for errors, so they also have to discard those rounds because those bits are now public. So in the end, they are left with this final key. But for this key, they are now sure that they both have the exact same key bits. They are sure that no adversary has information about this. And that, of course, also the bits are perfectly random. So this is something they can then use for this one-time pad encryption to encrypt their messages. Of course, now they can only encrypt a message made of 4 bits. So in general, you have to run a lot of rounds to get a reasonable amount of key. And here, in my choice of outcomes and bases, I have been a bit generous. So you see, only 30% of the rounds they have chosen different bases. Usually it will be like around 50%. But also in a practical protocol, the number of rounds would be like millions or billions. So they get reasonable amounts of key in the end. Okay, so this shows that in case there's no adversary, the protocol works. So the steps that we have come up with, they will generate a perfectly secure key without an adversary. Now we have to check what happens if the adversary comes into this. Yes?
Excuse me, may you repeat, please, how the final key was found? I didn't follow this last part. I mean, after Alice checks the shared information and some qubits.
Yes. So after Alice and Bob have discarded the rounds where they have measured in different bases, they have this shared information. And now they check for errors. So Bob reveals these keys, and Alice checks if these are the same as her key. So in this case, without adversary, everything is fine. But of course, then you have to discard these bits because they have been made public. Bob has announced them over the public channel, so also Eve got this information. So they have to discard these bits. They can't use them anymore for the key. And what they use for the final key is then the part of the shared information that hasn't been revealed. And this way, these bits here form the final key. Yes?
So you mentioned beforehand that for this to work, the classical channel should be authenticated.
Mm-hmm.
First, what guarantees that this is authenticated theoretically, and even if we want to implement that? And second, if it was not authenticated, how would that would this protocol fail, and where does it fail?
Okay, maybe I start with the second one. If the channel wasn't authenticated, then Eve could just impersonate Bob. So she could just intercept everything here. And like she could get the information from Alice and just send completely different information to Bob. So she, for example, like she could tell Bob like that. So Alice has to, the classical communication Alice has to do is say which rounds they measure in the same bases. So what Eve instead could do is tell Bob in which rounds she and Bob have the same bases. So she could just basically establish a key with Alice and Bob separately if she could intercept this classical communication, because Alice and Bob wouldn't notice they're communicating with a third party. And then how it can be ensured is, so there are different ways, but of course it doesn't come from nothing. So it is possible to implement this like with classical methods in an information theoretically secure way, so without making any additional assumptions, but you need something to start with. So you, for example, need a short like password that Alice and Bob share, because something needs to distinguish Bob from Eve. Like from Alice's point of view, she needs something that distinguishes the honest party from the dishonest party. That could, for example, be a short password. It doesn't have to be a key, so the requirements are lower than that, but there needs to be some seed for security. Or it could also be a third party which like verifies that users are honest. Like if you have a large communication network, that's also what we have nowadays classically, that there are third parties that tell you, okay, this is a secure website, for example. So if you would imagine a large quantum network in the future, then there would be parties that validate the honesty of other parties. And in practice, like the actual protocol that would run, one way is to use hash-based protocols. So you send the message, and you also send a hash of the message. And then it's so if so Bob can verify that this is the correct message by computing the hash of that message. And it's so if the message slightly differs, then the hash would be completely different. So it's basically impossible to break this. But yeah.
Even quantumly, it's impossible.
Even quantumly, yes. Yeah. And one addition to this, you could also do it with like an authentication procedure with computational assumptions, like using something like the RSA algorithm, because the issue here is not that bad as for encryption. This authentication, if you use RSA, which relies on computational assumptions, it would have to be broken in real time. So the problem with encryption is that the adversary could just store everything that's encrypted with RSA and break it in the far future when quantum computers are available. But this authentication procedure would have to be broken right now. So you could say, okay, today I believe that no one can factor a large number, so I use RSA for authentication and I'm happy. Because after the protocol is finished, it doesn't matter if the adversary could decrypt this information later. So you could say, you could argue for having computational assumptions for the authentication procedure. It's not as strong, but it's you could argue that this assumption is valid. Yes?
So I think in this case you don't have to use entanglement because the source is in Alice's lab.
Mm-hmm.
She can just create 0, 1, plus 1.
Yeah, true.
And send it. So
Mm-hmm.
entanglement is useful in BB91, but in BB84 you don't need it.
Yeah, you don't necessarily need it for BB84 because instead of generating the entangled state and measuring Alice's part, you could just directly randomly create 0 and 1. Yeah, it just shows this presentation to connect it better to what we've seen before. And sometimes it's easier to have this entangled picture for the security analysis afterwards.
Okay.
Okay. All right. Okay, so this is one example of a protocol that is based on a prepare and measure scheme. So quantum state is prepared and measured. There are other schemes that are called entanglement based, where you have some source here in the middle controlled by the adversary, which sends entangled state to Alice and Bob. So the next step is to look at what happened if the adversary intercepts the quantum states, if the adversary tries to attack the scheme. But I think at 10:30 we have a break, so I would like to do this after the break to not have to interrupt it. So now we still have 5 minutes, so if you have any other questions that you would like to ask about anything I've presented before, then this is the time. Yes?
So initially you mentioned you can use quantum networks to do shared computer, like to compute on a server without the server actually gaining the contents of this information, and you mentioned that's impossible classically. So do you know about fully homeomorphic encryption?
Well, little.
So I mean, the idea would be to just have an encryption scheme where you can compute on the encrypted content, and it will do the same to the underlying content. So you can encrypt it, send it to a server. The server computes, sends it back, and you decrypt it, and you gain the result of that computation.
Yes.
So wouldn't that be the same?
But I'm really not an expert on this, I have to say, but wouldn't the server learn about the kind of computation they're doing?
Of course, you have to tell the server what operations to perform in a sense, but the server doesn't know about the data, the information, and like you have kind of the same constraints as with quantum computation, where like you cannot do if statements, branches, you cannot remove information or add it to the system, so you have to kind of just shuffle things around.
Okay, I see. Yeah, okay, I don't know so much about that. That's possible that that works, yeah. Yes?
Yeah, so I was wondering if there are any other protocols which would, probably address some of the disadvantages of this, because for now this looks like it works perfectly fine. But are there anything we are missing out on? Any disadvantages or any physical constraints?
So one issue with this is that it relies on having perfect qubits. And this is, of course, practically, you never have perfect qubits. If you implement it, for example, with photonic sources, this would require perfect single photon sources, which don't exist. So there are protocols that adapt for this, and that instead of having these perfect qubits, they use coherent states already on the theoretical level. It makes the analysis much harder, it's quite painful, but it's closer to reality, and in that sense also provides more security because it captures the actual implementation. Yeah, but there are a lot of efforts of designing protocols on the theoretical level that are already closer to what you have in the lab. And there are also protocols that try to increase the efficiency, for example, by adding more measurement bases or changing the ratio of how much you measure in different bases. Yes?
Could you, now this protocol is given instructions like the X basis and the Z basis. Could you also include the Y basis in the protocol? And does that have any advantages for security or this computational advantages?
Yes, there is actually an extension of this protocol that also includes the Y basis, called the 6-state protocol, because then you have 6 possible states. And it does have some advantages. So I think in certain regimes or so, you get a bit more key. Like the key rate that you calculate in the end, you get more key from the same number of rounds. Yeah, in that sense, it's a bit more advantages in terms of key, but of course, practically you then have to have devices that encode more bases, which might be a disadvantage. I don't know. I'm not an experimentalist. But it isn't as widely used as this one. Sometimes people even like remove, so here, sometimes they even remove one of these bases on one side. So they only have, in the end, 3 states instead of 4, because it's sufficient for security, and experimentalists find that more practical. Yes?
I was wondering that here, if I'm not wrong, we are only using like the computational basis and the horizontal basis, right? So if we sort of introduce like, say, one more set of bases, and say Alice and Bob can measure one of these 3 bases, does that increase the efficiency and make it harder for Eve to sort of gain something, or does
so that's like close to the previous question of if I add the Y basis, it doesn't really, like, it makes it harder for Eve to get information, but it also makes it harder for Bob to select the same basis as Alice. So Bob's, like Alice, the number of rounds in which they both have the same basis is reduced, but also the number of rounds in which Eve could guess correctly is reduced. So it's a disadvantage for Bob and Eve, basically. In that sense, it doesn't help, but it does, in some cases, increase the key rate a bit. Right. Okay, yes?
I didn't get the previous question regarding the entanglement, so why isn't it needed? Or what was the question? Maybe you can repeat it again.
So the thing is, the way I presented the BB84 protocol is, I said Alice prepares this entangled state. But actually the original description was that there wasn't any entanglement needed at all. So equally, Alice could just like remove this whole quantum part on her side, or like she doesn't need to measure the quantum state. She could take a randomly generated bit or 2 randomly generated bit and encode these bits in a quantum state, which is then sent to Bob. So she doesn't need to, it's just a single qubit state in that case. And that would work equally well. I just wanted to use like the description with entanglement to connect it to what we had before. Okay, so if there are no more questions for now, I suggest that we go into the break. Then I'll see you again at 11. So let's get to the second part of the lecture. And now we want to see what happens when this BB84 protocol is attacked. So you see we had all these nice steps that Alice and Bob, they measured. They prepared quantum states, they measured them, they checked errors in the outcomes. And I forgot to add this. This is the classical part of the protocol.
I think that's what I
meant. Yes. So now we have seen everything works perfectly well when there's no adversary. So the protocol works in principle, which is the first thing you should check with a protocol. But now, of course, the adversary is not inactive. The adversary will do something. So, what happens if the eavesdropper intercepts the quantum state? Okay, so let's go back to the protocol and see what she can do. Okay, so we have seen in the calculation before, it's here, that if Eve intercepts the quantum state and does some measurements, she will introduce errors. So Alice and Bob no longer see the same measurement outcomes when they measure in the same basis. That means on this stage, Bob's outcomes will be slightly different. So let's say here, instead of a 1, he will see a 0. Say here also it's disturbed, and here as well. So this is Eve introduces errors. Okay. Move this a bit. Okay, but Alice and Bob, like, they continue the protocol. Now Bob's outcomes are just slightly different. That means after they have compared the bases and checked which are the same bases, the shared information is not exactly the same for Alice and Bob. So it's not exactly shared. Because here, for the second bit, Alice will have a 1 and Bob will have a 0. And also here, they have different bits now. But at this point, they don't know it yet. Okay, then they check for errors, so Bob revealed some of his bits. That means for the second bit, instead of the 1, he will reveal the 0 that he saw. And then Alice sees, oh, an error has occurred. This 0 is not the same as the 1 that Alice has. So she will tell Bob, well, here we actually don't share the same bit. The other ones are still fine. See, here we had some errors. And here we have the detection of the error. Okay. And then, so now Alice and Bob, they have this information. Okay, there must have been an adversary because we have seen some errors. So from this detection of errors, they have gained some information. So they see the observed error rate. So Alice checks, in one of 3 cases, she has a different bit than Bob. So the observed error rate is 1/3. And since we know the actual error rate in the whole string, we can see that, okay, there have been 7 bits, and in 3 of them, there's an error. So we know the actual error rate is 3 out of 7. So the actual error rate is a bit higher than what Alice and Bob have observed, but of course this is a very finite example with 10 bits. So if you have more data, these 2 numbers get closer together. Then if the error rate is too high, they will abort the protocol. But if it's in a beyond below a certain threshold, then they can still continue with classical post-processing, with error correction and some privacy amplification that makes this imperfect bit string into a perfect key. I'm not sure into how much detail I can go about those procedures, but it's just important to know that it's not necessary that Alice and Bob already produce perfect bit strings. There are ways with classical post-processing to make imperfect bit strings into perfect keys, as long as this error rate is not too high. So, to get the final key in this case, I need to do some classical post-processing. So this is purely a classical procedure. And it is only possible to get a perfect key via this classical procedure because we know how much the adversary knows. This is like the most important difference between classical and quantum cryptography, that we know how much the adversary knows, so we know what classical post-processing to do. In principle, like everything here is now like classical. We have classical bit strings and do classical post-processing. But in classical cryptography, you don't know how much the adversary knows, so you don't know how much post-processing you have to do. In the quantum case, we know exactly, or we can bound how much the adversary can know, so we can do this classical post-processing. Okay. Okay, so this is how it works in the presence of an adversary. So how Alice and Bob see the errors in the protocol, and then that they can turn the imperfect bit strings into a perfect key. And next I want to shortly tell you a bit about experimental implementations. So you get a bit of a feeling like what's happening in the real world and what are the challenges and how people actually implement these kind of things. So okay, so generally we have like 3 goals when we implement a QKD protocol. We want to have high key rates because we want to use the key to encrypt some data that we have, so we need a reasonable amount of key for that quickly, usually. And ideally, we would like to match key rates of classical cryptography. So we'd like to have something of the order of 100 gigabit per second. That would be cool. Then we want to go over large distances because if we might want to encrypt data that we want to send to someone on a different continent. So we don't want to be restricted to small distances. We want to be flexible with who we communicate. Let's say it would be great if we could do something on the order of several hundreds of kilometers. And then we want to have a high level of security. And I tell you a bit more about what I mean with high level of security. It basically means we want to have very few assumptions about the devices that are incorporated in our protocol. So what we had here in the BB84 protocol, it falls under the name of device-dependent QKD, because the security of the protocol depends on that our devices behave exactly as I described it here. So we exactly have qubit states, and the measurements also exactly do the Z and X measurement. So this is... That means, so the trusted part of our setup is almost all of it. We have to trust that our measurements do exactly what I said they're doing, that they measure X and Z and nothing else. And we also have to trust that the Hilbert space dimension is what I said it is, like that we have qubits. And this is actually a very weird thing to trust, that the Hilbert space that describes my quantum system conforms to the dimension I impose on it, because it's not a physical thing I can enforce. It's the mathematical description. So in practice, I can never be sure that my Hilbert space dimension is 2. So this is actually quite a strong requirement. And there are, in fact, explicit attacks that you can do if you allow the adversary to use higher dimensional Hilbert spaces, if you allow them to use qubits instead of just qubits. The untrusted part of device-independent QKD is basically the quantum states. Because we allow the adversary to attack the quantum state that is sent over the channel, so we don't need to trust this quantum state. Okay, this is the most trusted version of QKD. We put a lot of trust into our devices and what's happening here. Then there's the other extreme, which is called device-independent QKD, which is where we have the least assumptions. So like if you remember this picture that we had before in the presentation, where we had the scheme that we have assumptions, then a security proof, and then a security guarantee. Then what I'm talking about here is what assumptions I need to put into the proof for it to work. And it's important to remember that the security guarantee only holds if the assumptions are fulfilled. So whatever I put in, I need to be really sure that it is fulfilled, otherwise it might compromise the security. So these kind of assumptions are actually quite a high requirement. And since there have been found explicit attacks on these assumptions, people have come up with device-independent QKD to remove this weakness. And there's basically no trusted part for the quantum devices. So this has to be taken like a bit carefully, because the classical parts, the random number generator and the classical computer, they always have to be trusted. Okay, but on the other hand, what you don't have to trust is, again, your quantum states. You don't have to trust your measurements. And you don't even have to trust that the Hilbert space dimension has a certain value. Basically, the whole quantum part is just a huge black box that you don't need to characterize in any way. You don't have to trust it at all. This is very nice, because then your assumptions here, they are very weak. And if you have very weak assumptions, then they also cannot be attacked. So this is basically the highest level of security that we can achieve, but it's super hard to achieve. I'll show you some data for that a bit later. And you see that even though we would like to have these kind of protocols, practically they're incredibly difficult. And then there are things that are somewhere in between these two extremes, where you trust part of the equipment and you don't trust other parts of the equipment. So there's like measurement device independent QKD. Where like you don't trust your quantum states or your measurement. That's why it's measurement device independent. But you still have to trust the Hilbert space dimension. And I find this actually one of the weirdest requirements to trust, because it's in the mathematical description of your setup and not really a physical property that I can enforce. And then the other setting would be source device independent QKD. Where you trust the measurements, but like not the Hilbert space dimension of your quantum states. So these are the main categories of QKD protocols. But of course, you could come up with any sort of combination of trusting things and not trusting things. You could also say, okay, I trust the equipment of one party, but I don't trust the equipment of the other party for some reason. So between device dependent, device independent, there's a zoo of possibilities that you could explore. But of course, like you can decide what assumptions to make, but then you need to find a way to actually do this proof based on the assumptions. That's the hard part. You would like to remove assumptions, but that makes the proof harder. Okay, so these are the different kinds of categories, and I want to show you some data what these different protocols can achieve nowadays. This. So here, this is an example where people try to investigate what is the longest distance that we can achieve. How far can we go? And this is in this category of device-dependent QKD, so they trust all the equipment. And this is the work from 2018, which is an optical implementation, so they used photons to encode the qubits. And it's fiber-based, so there's some fiber here that connects Alice and Bob. So I won't talk about the experimental setup in detail, but for people who know these kind of diagrams, that might tell you something. The important thing is just that we have photons that are sent via fiber, and then the protocol is basically the BB84 protocol I showed before, with some small adjustments to improve security. Then you see the diagram that tells you the distance on the x-axis. And on the y-axis, you have the secret key rate, like the rate of key that you get out of it. This is the number of bits you get per round of the protocol. No, per second, sorry. This is the number of bits you get per second from this implementation of the protocol. And you can see, like at 250 kilometers distance, they're at, I don't know, something between 10 to the power of 3 and 10 to the power of 4, which is not bad, but it's still orders of magnitude away from the gigabits per second that you would like to have ideally. But you can also see that it decreases quickly when you go further. So the longest distance they could achieve was 421 kilometers, and their key rate was below 1 bit per second. So that's not really practical. So this shows like the limits of distance that we roughly have nowadays when you use a fiber-based implementation. And they really put a lot of effort into using long distances. Like they use these ultra-low loss fibers, which you don't widely have in communication networks. Like those are expensive and specific. So this is really, they put in all the money and effort to see how far can we go before the key rate drops to 0. So we are at 421 kilometers with very little key rate. And then another implementation used satellites instead. So that was also from the same year. It's also optical, so they also use photons, but now you have 2 ground stations that communicate with a satellite. And one was in China and one was in Austria, so that's quite the distance. They could achieve, like, let's say, non-zero key rates. So they have here 9 kilobit per second at 600 kilometer and 3 still at 1,000 kilometers. But using a satellite is, of course, a bit tricky because you have to, like, this is still device dependent, so you have to trust all the equipment. And your satellite is basically a trusted intermediate party. So you fully trust that the satellite operates perfectly and that no one attacks the satellite. So you fully trust the satellite. And it also depends on like weather conditions and the position of the satellite. Because the satellite orbits Earth. So there's a limited time window over which it can communicate to the ground stations. So what it does is like it orbits the Earth. When it is connected to one ground station, it establishes a key. Then it goes to the other ground station, establishes a second key, and then when he comes back, he can like distribute keys between these stations. But it's orbiting the Earth and has limited time windows, so it's not as flexible. You would need many satellites which have to communicate with each other to make it more flexible. And this is, of course, incredibly expensive. But also, like fully trusting the satellite, the thing that's flying in the orbit, is maybe a huge assumption that you not necessarily want to make. But yeah, it was quite impressive that they could actually establish this QKD link between parties that are over 7,000 kilometers away. And then they used the key that they generated to actually encrypt a video call between the two stations. Okay. And the nice thing with satellites is that, like in the optical fiber, of course, you have lots of losses of your photons, but with a satellite, there are less losses because the atmosphere, you don't have so many losses, especially in the higher parts. So it's actually preferable to have free space communication. Okay, so these are some examples, and second, I wanted to show you also something about device-independent QKD as a contrast, but now I forgot. Yeah, here it is. So there are some experiments about device-independent QKD. So it took a while until this actually had been demonstrated practically, because what you need as a basic requirement for device-independent QKD is a loophole-free Bell test. So that's already a huge experimental requirement. So since loophole-free Bell tests have been implemented, since then it still took a while until device-independent QKD, based on that, has been realized. So these are all from 2021. And there are basically 3 groups who did it more or less simultaneously with different platforms. So one was photonic, again, and other ones used trapped atoms or trapped ions. And I want to show you a bit like the numbers they could achieve here. So the distances they could achieve are like tiny compared to what we've seen before. The first experiment in Oxford, it could achieve 3.5 meters distance. So it was like basically one optical table where it was sitting on. The photonic one in Hefei in China was 20 meters. And the one in Munich was 700 meters. This paper was actually called a device-independent QKD system for distant users. And distant was 700 meters. So this is like the record that we have. But you can also see the key rates that are connected to this. These are super small. Like here we have 3.37 bits per second. In Munich we only have 10 to the power of -4 bits. So for distant users you have like almost no key. The one in China, the photonic one, could at least get 466 bits per second. But you see, before that, we had at least like kilobits per second over like thousands of kilometers in the satellite experiment, or even hundreds of kilometers in the fiber-based one. Compared to that, these numbers are really very tiny. So there's a long way to go if you want to use this high level of security. There needs to be a lot of improvement to get higher numbers here. And the biggest issue is in all of these cases that we lose photons, because communication always happens via photons in optical fibers or free space in any sort. And photons are so susceptible to loss that, all this loss makes it super hard to get high key rates over long distances. Okay, so that's basically like some idea of the state of experimental implementation for you. And as the last part of my lecture, I want to talk a bit more about the security of QKD. I want to talk a bit more about what security means and how we can show it and on what assumptions it is based. Yes?
So could these protocols, the QKD protocols, be used as for sensing, for example? Like rather than having Alice and Bob, like 2 communicators, human beings, we would have quantum sensors so that we can sense different stuff simultaneously or so. Because I've seen some like sensing using quantum optics mainly with squeezed light and so on, which have very similar, let's say, setups and so on.
I guess for quantum sensing, you don't have as huge requirements regarding the secrecy, right? So I'm not sure if QKD itself would be beneficial. Maybe Bell tests could help, but I don't think you need the secrecy property of QKD for sensing. Okay, so then let's look a bit into the security of QKD. Okay, so we had this scheme before that we have assumptions on which we base our proof, and then we get a security guarantee. Yeah. So the goal of this is that we get a mathematical proof that the QKD protocol is secure. So from this proof, we can then really be sure that the security guarantee is fulfilled if the assumptions are fulfilled. Because the mathematical proof does not leave any room for exploitation of the adversary. It's really just mathematics. Okay, but if we want to have a mathematically rigorous proof, we first need to have a definition of security. Like we need to know what the security guarantee is in a mathematically rigorous way. So we need to write down some equation that has to be fulfilled that we can then prove with a mathematical proof. And this is really the heart of a lot of the theoretical work that is done on QKD. It is investigating how we can prove the security of different kinds of protocols with different kinds of assumptions. Because if you change the kind of assumptions that you put in, you might need different proof techniques. Not all proof techniques work for all assumptions and all protocols. So you really have to be creative when designing a security proof here. But the first step is to say, what actually do we mean by security in a mathematical way? And here you need to be sure that the mathematical object you define, it really captures the properties that you want to achieve. It really captures the functionality that you want to build. So the idea is that you say, you define what the perfect functionality is that you want to achieve, and then you compare the protocol, the system you build with your protocol, to this perfect functionality. So and what do I actually mean when I say this? So first, let's recall what we want to achieve. We want to have a device that outputs perfect cryptographic keys. So it was supposed to be uniformly random. Identical for Alice and Bob. And private. Yes. So the ideal system here would be some sort of box that outputs keys for Alice and Bob. And then let's say the lower interface is for Eve, and she does not get any information. And this ideal system would put out these keys, Ka and Kb, this key pair, such that the properties 1 to 3 are fulfilled. In contrast to this, you would have the real system, like the one that we are constructing with the protocol we're interested in. So it's also some sort of box that outputs keys. But as we've seen before in the protocols that we design, typically there's some information that goes to Eve, and she might also be able to tamper with things in the protocol. And the whole system is described by the states that we're using, the measurements, the channels that appear in the description, and everything that makes up the protocol. Okay, and now I want to compare these two systems. And since we're our description of the world is based on quantum mechanics, what we compare here are the quantum states that describe the outputs of the system. So the real system is described by some quantum state on these registers Ka, Kb, and E. And we can say something about how the state looks like from the protocol that has been designed. And the question is then, how close is this real state to the state that describes the ideal system? So how does the ideal state look like? So we have also on the same registers. Okay, the ideal state needs to capture all these properties that we would like to achieve. And I will first write it down and then explain why it captures all these properties. Okay, so here we have a state on the systems on Alice's key system, on Bob's key system, and on Eve's quantum system. And these entries here of Alice's system are like classical keys encrypted in a quantum state, because we want to describe everything with quantum, like not encrypted, encoded in a quantum state. So this K would correspond to something like this. So this is the whole key. And here we go over all the possible keys that could be produced by the protocol. And you can see we have here Alice and Bob always have the same key. It's the same K that is in this quantum state. That means you have the property that the keys are identical, encoded in these states. We also know that, so here we have a tensor product with the adversary. That means the adversary is completely uncorrelated with the keys, so she doesn't know anything. And lastly, the third property, the randomness is encoded in here, because this is the weight that each of the key values has, and it's the same weight for all the keys, because it's so 2 to the power of L is the number of possible keys. So each key value is equally likely. So this is the ideal state they want to achieve. If the quantum state that comes out of our protocol is close to this state, then we know it has the desired properties. So the goal of the security proof is to show that this real quantum state, we have created with our protocol is actually close to this ideal quantum state. Okay, and when we say it is close to the state, of course we need to say something about the distance measure. So what does it mean for two quantum states to be close? There are different distance measures that you could choose when you compare quantum states, and you need to choose one that is operationally meaningful for the task that you want to achieve. So something that really tells you in this cryptography setting, this distance measure is a meaningful one that ensures the security of the protocol. So, let's see. Okay, and the distance measure that we use in QKD is the trace distance between two quantum states. So do you want to show us that this distance between a real and ideal state, which is given by this. Okay. Okay, so this is the distance between the quantum states that we use, and we want to show that it is small. Ideally, we would like to show that it is zero, that the ideal state is exactly the same as the real state, but that turns out to be basically impossible, that having them exactly equal. It is much easier to show that they are extremely close. So you can show that the distance is like 10 to the minus 20, but it's almost impossible to show that it is zero. But you're probably fine with them being like at a distance of 10 to the minus 20. Because if you look at what the interpretation of this distance is, then you see that allowing a tiny error is fine for all practical purposes. So let's see why is this a good choice? Because of the operational interpretation of the trace distance. It means that this distance, this trace distance between two quantum states, it quantifies how distinguishable the states are. And this is meant like fundamentally. So if you have access to all possible operations on these states that you could perform, all the possible computational power or everything, you can do whatever quantum mechanics allows you to do. This distance tells you how well you can distinguish them. You cannot do better than what the distance tells you, no matter how powerful you are. And another nice property of this distance is that the distinguishability doesn't get better if the key is used. So what I mean is that so if you apply some sort of quantum channel, some sort of operation on these states, this can only decrease the distinguishability. So you can interpret this in a way that, so this distance tells you how secure things are, and then this operation here, this could, for example, be using the key in a one-time pad. So it tells you if you use the key in any sort of encryption procedure, it doesn't get less secure. Because this, in principle, could happen, right? What we said before, it doesn't tell you anything about what happens if I use the key. So it could, in principle, up to this point, still happen that I have a almost perfectly secure key, but when I use it, it becomes imperfect. But this property of the trace distance guarantees you that it can only get get less distinguishable. So it doesn't, using the key doesn't compromise its security, which is a basic requirement you want for the key. Yeah.
So is this trace distance something similar to the fidelity, or
it's not the same, but they're related. Like you can bound one with the other. But the trace distance has nicer properties. Okay. And so this is one way of interpreting the trace distance, and there's another one. So the takeaway of this is that using the key doesn't make it less secure. And you might think that this is like a trivial thing, an obvious requirement, but actually historically this wasn't the first way to define security. The first security definition we had for QKD was based on mutual information, and that one actually didn't have this property. So there you could show that once you use the key, it actually becomes insecure. So the key was perfectly secure as long as you didn't use it. And we want to avoid this. So this property, while it may seem obvious that we want it, historically it wasn't actually that obvious. So, and the second interpretation of this trace distance is you can interpret it as a failure probability of your protocol. So you could say, if you show that, so you have the real state and the ideal state, and you can show that the distance between them is epsilon, some small number. So that means it tells you that the protocol you're looking at, with the probability that it outputs the ideal state, is 1 minus epsilon, and the probability that it outputs the real or not the real state, like not the ideal state, is epsilon. So you can be sure that in 1 minus epsilon %, your protocol behaves identical to an ideal protocol, and in epsilon % of the cases you don't know what happens. You don't make any guarantee. And this epsilon, it could, for example, be 10 to the minus 20. So you see, if you allow for this tiny error probability, you still have the guarantee that in basically all of the use cases, you get the ideal protocol. Only in very few cases you don't get it. But you're fine with that, because it basically never happens. So with the choices of epsilon that people typically make in these protocols, this is usually the same or even better level of security than nuclear power plants. So if you make some calculation, like you calculate the probability that a QKD device outputs an insecure key in its lifetime, then this probability is smaller than the probability that a nuclear power plant, that there's that there's an accident in a nuclear power plant in its lifetime. So you can achieve very high levels of security with this. Okay, so to summarize the security definition that we now have. So we say that a QKD protocol is epsilon secure if this distance between the real and the ideal state is smaller or equal to epsilon. Okay, so this is the starting point for the security proof. This is the objective that we want to show. And you can make it a bit easier, like you can split it into two properties. Sometimes that's easier to prove. So you can split it into two separate things to prove. One is the correctness of the protocol, which means that the probability that the keys are not equal, this is smaller or equal to some epsilon for correctness. And the other one is the secrecy. It says that the distance between Alice's state, like a state on Alice and Eve's system, is close to a perfect one. And if you show these separately, then you can show this fulfills the above definition with an epsilon that's bounded by the sum of the two. Yeah. And sometimes this is easier to prove than the thing above, because here in the secrecy one you have removed one quantum system, you only have to care about Alice and Eve, and it could be easier to prove these things separately. But of course, like the challenge now is that you have your protocol and you have the information gained in the protocol, so you basically know the error rate. And from the error rate you now have to show that this property is fulfilled, that these quantum states are close. And that's then where the security proof comes in. Okay, before I say some more details about the security proof, I want to talk about the part in the scheme. Is it here? That says assumptions, because now we have the security guarantee, but it needs to start from some assumptions. And here it's very important to be clear what assumptions you actually put into the protocol, because sometimes people say that like the security just comes from the laws of physics and that's it, but that's not actually true. We need to put in a few more assumptions for it to work. And it's important to be clear about these assumptions, because if one of them is violated, then the security guarantee doesn't hold anymore. Okay, one of them we already encountered before, and that is that Alice and Bob have to have access to this authenticated classical channel. And as I explained before, there are different ways to achieve this, for example, with an initial password that they share, or also with computational assumptions. But however we choose to realize this, we have to be clear about what assumptions this adds to the whole procedure. And then another very important aspect is that the labs that Alice and Bob have, they have to be isolated. So here in the BB84 scheme that we had, here, these labs that we have, like Alice and Bob, they have to be isolated in a way that no unauthorized information can leave the labs. Because, for example, what Alice and Bob store in the labs in this classical computer are the outcomes of the measurements. And they need to be sure that these are not like secretly leaked to the adversary. And that's an assumption that we make, that the lab is sufficiently isolated. And also, it can actually get very tricky, this assumption, because, for example, like the lab naturally has some points where something can enter. Like, for example, Bob, he needs to receive this quantum state. So, and then he receives the quantum state and he measures it. And then he needs to make sure that at this point where the quantum state enters the lab, the adversary cannot use this hole into the lab to retrieve some information. For example, there are actually like practical attacks where the adversary can just shine bright light into this opening to mess with Bob's detectors. So it can be quite tricky to ensure that this isolation is fulfilled. For example, Bob could first receive the quantum state, then shut the lab, and then do some measurement. So, but yeah, it's not. It sometimes takes some effort to ensure that this assumption is actually fulfilled. Okay, then what also comes into the assumptions is the level of trust in the devices. Like that's what I explained before with the different kinds of protocols, device dependent, device independent. And of course, also your like this device dependent, device independent, etc. And also the trust in the classical devices. So trust in the random number generator and the classical post-processing. Like the classical computer. And here as well, in a practical implementation, there come more tricky details. Like, for example, if you have if you do a device-independent protocol and you have to implement a Bell test for that, you don't only have the quantum states and measurements that are happening in the experiment. You also have classical parts of the experiment that, for example, take care of timing and these things. And you have to realize, like, you have to remember that all of these devices are also part of the trusted part of the setup. And then a very fundamental assumption that we make is that quantum theory is correct. Of course, the whole proof and everything depends on quantum theory. So for this, basically, like we don't need all of quantum theory. As I said, time evolution is not really important here, but we need to assume that the way quantum states, the state space of quantum mechanics is described is correct description of nature. Now you can, of course, start to ask questions about like what happens with quantum gravity, for example, when we know that like somehow if you want to unite quantum theory and gravity, somehow some things will have to change in both theories probably. So that might change the way quantum theory describes the world. And of course we don't know what's happening there. But since the way quantum theory is formulated nowadays accurately describes the experiments we use for quantum cryptography, we could hope that the relevant parts for quantum cryptography are not really affected by quantum gravity. Because it's the effects we can expect that gravitational effects don't really have an influence on what we need for the security of quantum cryptography. But of course we don't know. We have to see. Yes?
So by relevance you mean, for example, the no cloning theory?
Yes, exactly. The no cloning theory, monogamy of entanglement, these have to be fulfilled. Yeah. Yes?
Is it relevant if we assume that we can have a different number of adversaries, or would that affect the kinds of protocols we might use?
Not really. Like, it could make things easier. So at this point, we have one adversary that is responsible for everything. So the knowledge and the power is united in one adversary. You could make a less powerful assumption. You could say there are two adversaries that cannot communicate or something, only have restricted access to certain parts of the experiment. But the way we have described it now, with one adversary that controls everything, is the most paranoid one. Our theory is correct. And there are another assumption that we make about quantum theory, and that is complete. And that means there's no other theory that confirms the predictions of quantum theory that has a higher predictive power. For example, there's an encryption scheme that is based on thermodynamics. That is the Quiche cipher, where within the theory of thermodynamics, this cryptographic scheme is perfectly secure. Like, you can encrypt messages with it that no one can read, that only has like powers allowed by thermodynamics. But when you then extend this and say, okay, the adversary could in principle also have all the powers allowed by quantum mechanics, then the scheme becomes insecure. So that would be a counterexample for a theory that is not complete. Because within thermodynamics, everything is secure, but as soon as you allow the theory of quantum mechanics, then the scheme becomes insecure. So that's something we want to avoid. And we can actually prove that quantum theory is complete if, from the assumption that it is correct. And we have to add that something like randomness exists. So this is not necessarily an assumption in this setting, because we already assume randomness exists with the random number generator. So from the fact that we assume we have a random number generator and quantum theory is correct, this already implies that it is complete. Okay, so you see there are a number of assumptions that we have to put into the security proof, and the most important thing is that you list all the assumptions that enter the proof, so then you know what parts you have to trust to have your security guarantee. If you want to trust these parts, that's then a different story. Okay. So for the end, I want to say a few more words about the security proof. I will not have time to go through everything, I think. Let's see. Okay, so as we've seen, the protocol, like the BB84 protocol, and all other protocols follow the same basic structure. So there's this quantum phase, and at the end of the quantum phase, there are some raw keys. Let's call them R for Alice and 1 for Bob. And these are partially correlated. So they're partly the same for Alice and Bob, and also partially secret. Eve has some information on it, but of course she doesn't know everything. Otherwise, or if she knows everything, they would detect it and abort. Okay, then the first step that Alice and Bob have to do is parameter estimation. That's what I showed you before. They check for errors. They need to get an estimate of how much the adversary knows. So first, parameter estimation. And this will provide them with an estimate of Eve's knowledge. Okay, and then once they know how much the adversary knows, so now they know how many errors there are, and from that they infer how much the adversary knows. The first thing they can do is they can perform an error correction protocol. And afterwards they have new strings, which are now the same. I call them KA tilde and KB tilde. So they're now the same, except with a tiny failure probability. And then, lastly, they do privacy amplification. This will remove all the knowledge that the adversary still has. So after the privacy amplification step, Alice and Bob have, again, new strings, where this property that they're equal, it still holds. This is not messed with by the privacy amplification protocol. And the keys are now uniformly random and completely unknown to Eve. Of course, except with this tiny error probability. Okay. All right. So let me say a few words about the error correction procedure. Yeah, I think that's a good idea. Okay. So I'll say a few words about the error correction procedure and also the privacy amplification. So for the parameter estimation step, Alice and Bob, they will look at the errors, and then from that they will infer how much information the adversary has. And of course, this can, this doesn't work perfectly because they only have a finite sample, a finite set of the full string. But you can, with statistical methods, you can bound the error probability. So you can say, okay, I've seen 10% of errors, then the probability that the remaining bit string has a higher error percentage is like bounded by a very small number. So they are almost sure that the errors they see represent the errors in the string. And you can then optimize how many rounds you use for tests to make this probability very small, that the errors you see don't represent the actual errors. Okay, and once they know this, they can do an error correction procedure. And this is a completely classical procedure. So you can use your favorite error correction protocol to perform this. It doesn't matter at all what procedure you perform, because after the procedure has been completed, Alice and Bob check whether it has been successful. That's the most important part. There's, you can use your favorite error correction procedure. And independent of what you did, so that's why usually in QKD people don't really talk a lot about the actual error correction procedure, because there are people in classical error correction who are experts on this, and we don't really care in QKD. We just say, okay, an optimal procedure would have needed this amount of information, and then we continue from there. But it's for the security, this is not a problem, because Alice and Bob can check whether it has been successful, and they do it in the following way. So for this, we need to use two universal hash functions. I'll just give you a definition of this, and then show you why this is exactly the thing that ensures security. Okay, so okay, so a family of functions that go from one alphabet to another is called two universal if the probability of collisions is very small. That means if you see like the output of the hash function for two different inputs, so if the inputs are different, then the probability that the outputs are the same is very small. You can create a family in a way that it is very small depending on how large the family is. That means that, okay, maybe I just show it. So if I want to use this kind of structure for the check of the error correction, you would do it in the following way. So Alice would choose, like Alice and Bob have agreed beforehand on this family of hash functions. They have a family of two universal hash functions. So Alice chooses one at random. She computes. So this is after the error correction protocol. So Alice takes her output from this protocol and computes the hash and sends this hash to Bob. Together with the choice of hash function. And then Bob computes the function on his part. And checks whether the two hashes are the same. Okay, so why is this a good idea for checking? Well, if Alice and Bob chose this function in a way that the size of the output alphabet is depends on the error they allow for error correction. So yeah, they choose it like this. Then you can calculate that the probability that the keys that Alice and Bob now have are not equal, given that the hashes are equal. Smaller than this error. So you see, this, what I've written here, is the scenario that Alice and Bob want to avoid. So this is, they have seen the same hashes, but their underlying keys are actually not equal. This is a bad scenario, because then they think everything worked well, but it actually didn't. This is what they want to avoid. And when choosing everything in this construction properly, then they know if they have seen the same hashes, then except with a tiny probability, their underlying keys are equal now. So in this way, independently of of what error correction procedure has been done, with this hashing check, they know with very high probability that it has been successful, and this is sufficient for security. Okay, and then just a very quick sentence about the privacy amplification step. So privacy amplification is then the step where Alice and Bob need to do a procedure that removes the information of the adversary. And actually, you can do it again with this two universal hashing, because there's a lemma that connects the hashing with the security definition that we had in the beginning. And I will just show you the statement, because I want to emphasize what kind of quantity you have to look at. It's called the quantum leftover hashing lemma, and it's really one of the most important lemmas that we have in security of QKD. And it tells you that if you have generated the final key from a leftover hashing function, so this is from a two universal hash function. Then the lemma guarantees you that this object that you want to bound for the security proof, so it comes from the security definition, it's bounded by these quantities. Like, this would be the length of the final key. Okay, so for the security proof, you won't have to show that this is small or equal to some epsilon security, and you see the quantity that is at the heart of this is this entropy, and I will not tell you much about it. Just it's called the smooth min entropy, and you're like, doing a security proof for a QKD protocol is basically calculating this thing. This is the object that you want to calculate, and there are like many different ways to do it depending on the protocol, depending on the assumption, and this is really where then research starts. You develop methods to evaluate this quantity based on what you've seen in the protocol. And I could like give a whole other lecture about how to do it, but this exceeds a bit the scope of this lecture. But this is really then what people in research are doing when they say they work on the security of QKD. They find methods to bound this quantity based on the protocol they have been looking at. And this could be like, there's numerical ways to do it, there are analytical ways, there's a whole zoo of possibilities, and not everything works for every protocol. For some protocols, we so far have no method that works yet. And sometimes it results in gigantic numerical optimization problems that you can't solve. So yeah, this is the fun part of the research. Okay, but this is so far everything that I wanted to tell you. Do you have any questions about what I've presented you now, before, at any point this morning? I also have I want to recommend you some books that, if you're interested in learning more about this, that you could check out. So there's something that's more generally about quantum cryptography. That is by Thomas Widdig and Stefanie Wehner, which is quite a recent book, and it captures more parts of quantum cryptography than just quantum key distribution. Like, it talks also about other protocols I've mentioned in the beginning, like this oblivious transfer, also blind quantum computing, and it gives a very nice, accessible introduction to the whole area. And it's I think so. It's born out of a course the authors gave at Caltech, and I think on the internet you can also find lecture videos about this. I didn't check specifically, but there's some additional material for students who want to learn about this that you can access there. And then if you want to learn more about quantum key distribution specifically, as it was mentioned in the beginning, I did write an introductory book about this that really focuses on quantum key distribution, and it doesn't assume much prior knowledge to it, but you basically need an understanding of linear algebra, and then it introduces the most important concepts that you need to understand quantum key distribution and security proofs in quantum key distribution. So these are the two main resources on quantum cryptography, specifically, that I can recommend if you want to go into more detail about this. And then, since I have presented everything I wanted to tell you, I think I will end the lecture already. And if you have questions, of course, I'm still available. You can ask me. But there's one last treat. So I was in Switzerland the last 2 weeks, and they have incredibly cute sheep in Switzerland in the mountains, and I wanted to share my favorite photo of the last 2 weeks with you. It's a Valais black-nosed sheep, and it's just amazingly cute. Look at this. Okay, thank you very much.